Jian Liu is going to talk about persistent interaction topology in data analysis. Are you ready, Jian?
So, thank you. My topic is persistent interaction topology in data analysis. This is the joint work with Dongchen and Wei Guowei. This work is mainly focused on the theory on application. So, what's the interaction? There is not a official definition, so we give you a introduction. Interaction refers to dynamic exchange and mutual influence between different components within a system. Uh, this this includes how these components influence each other. And understand the interaction is essential for comprehending the dynamic and behavior of a system across a variety of fields. There are several theories on interactions in topology or geometry. For example, the check homology. Check homology focusing on the cover with different open sets, the or um, or nerve complex. Nerve complex can often define on the cover or more generally it can define on a system with different components. This any two components have a relationship. Another homology called the intersection homology defined on geometry. This is to start stratific space by considering the allowed cycles with well-behaved intersection properties. So it can be regarded as a generalized of as the understanding on Poincare theory. But this theory or methods lack the description of interactive relationship. So they are not more strong to describe interaction. So we aim to study the interaction homology. We aim to study the interactions between topology space and describe their interactions using topology invariant. One potential approach is the interaction topology and developed in our previous work is the interaction homology and the interaction homotopy. And is another the notion of interaction cohomology was proposed by Oliver Kinnear. He has given the idea for us. Interaction homology can be regarded as the Euler characteristic of interaction complex. So it can be used to understanding Wu characteristics. So we'll give you a detailed and mathematical description. An interaction simulation complex can be regarded as a family of space or a family of simulation complex Ki, K1 to Kn. They should have the property that K equals to their union. Then we can also define the morphism between interaction simulation complex by morphisms such that there is a morphism K into L. This is the simulation map. And for each I, Fi, and Ki to Li is a simulation map such that Fi sigma I equals to Fj sigma j for if and only if sigma I and q equals to sigma j. This is the morphism that make the structure unstable, stable. So this is the interaction simulation complex and the interaction simulation map. So we can give you a chain complex. For interaction simulation complex, we have a family of chain complex C star for each ki. Then we tensor product order C star ki. This is a chain complex with the differential induced by the tensor product. This is a formal construction. Then we consider a subcomplex D star. D star is generated by the generators sigma 1, sigma 2 to sigma n, such that the intersection is empty set. This can be we can understand that this simplex has no common part, so we can prove that D star is a subcomplex of C of the tensor product of the tensor product. So we can make a quotient. The tensor product quotient the D star. This is the also a chain complex induced by the construction. So I C star is the interaction chain complex. The interaction homology is defined by the homology of interaction chain complex. This is the definition. And we can define the interaction between numbers. So we will give you an example. For example, consider the case figure 1a. This is the space. The red part is x. Red part is x s1 red at the black point. This is this is x1. This is x2. They all have an intersection part is the point. This is the same point. So they have a intersection part. So it is in our understanding of the usual homology, it is very trivial. But in the theory of interaction homology, it's not trivial. So in our theory, S1 is described by this simplex, and S2 have only one vertex. So we can compute the homology according to the definition. So the chain complex and the differential, this is the differential D1, and the cycles and the is this, and the boundary is this. So we can get the homology have two generator. This is generator 1, and this is the second generator. So So one can get the homology. Homology when p equals to 1 is k, k, and k, and otherwise is 0. This the then we'll give you a second example. And this is the standard n simplex. For example, for the case n equals to 1, this is the two, this is interval, and n equals to 2 is the triangle. For example, we'll see the picture, triangle. So it is a triangle self interact itself. So it is a triangle interaction of triangle. So we can compute its interaction complex. For us, this is the interaction chain complex, and this is its differential. So we can compute the bit number, and also we have its homology. So it is quite different with the Euro simulation homology or Euro homology. This is M for n equals to the homology. For n any n, we can have a homology for p equals n is equals to k. So homology can be computed. For the Laplacian also can be computed. So to define the Laplacian, we will have the interval product. So for two generators, their interval product is defined by this form. So we have the definition. This is the standard construction of interval product. So we can define the interaction Laplace by this formula. Why define the Laplace? Since the homology have the information or the features of homology is not enough for us to application in data science. So we will have a more have in Laplacian to obtain more information. So we can get a Laplacian. Moreover, we are developed the interaction homology and the interaction Laplacian to the persistent version. So this is our definition of persistent interaction homology. It is similar to the persistent homology in the Euro version. This is B. I'm sorry. So we can also give you a interaction in VR complex for a family of sets of points in space. We can define a VR complex by these forms, and then for we can get a filtration of interaction homology, and this is persistent homology. For the difference with above is that this construction is from the points, and this construction is also this construction from the simulation complex. Okay. We'll give you more example for this case. We can consider 2 point sites in a Euclidean space. S1 is 3 point, S2 3 point. You can see this 3 point is S1. This 3 point is S2. But as the distance equals to 0, then this 3 points S1, this 3 points S2, and S2 and the S1 have an intersection at these 2 points. So when the distance is this one is one, so this interval is the intersection component, and when the distance is square to this part is also the intersection component. So we can compute their Barcode for the interaction homology. For we have 3 cases for the union. For the this for the union, if we can't consider the interaction, we just consider the set one with the 4-point set. We can or we can see the union of the S1 and S2. The bucket is this. The intersection of X1 and 2, the bucket is this, and then the interaction bucket is this. So we can find that in the interaction case, the bucket have more information. So there is a H1 information bar, and moreover, in this case, we can read the persistence parameter 2 square at this is 2 square. But in the union or intersection of S1 and 2, their barcode are too simple. So we can define the persistent interaction Laplace. This is a definition construction. Property is that the persistent interaction Laplace, the kernel of the Laplace. This is the kernel of the Laplace. It is isomorphic to the persistent homology. So we are given applications. Consider closer compound. Closer compound have the 3 the elements and with different numbers, C, B, C, B, H. So we can divide it into 2 parts, C, B, and CH. So we can give for example, for this structure, okay, CB is this part, CH is this part. They'll have interaction part is marked in the figure, this and this. So we can compute the Laplace and then compute the eigenvalue of the Laplace. So this is the smallest eigenvalue in dimension 0. This is the smallest eigenvalue in dimension 1. So this is their features. So we will give an example for C2H3 BCH5. They have 6 configurations of this molecule. So there are 6 configuration have different energy. This is their energy. They have different, but we can see these 4 have similar energy, and these 2 have different energy. So we can also see their figures. This is the first 2, and this is the last 4. We can see that the distance are quite different. This is more larger. This is larger.
Yeah, Jian, can
Yeah.
you close in few minutes?
Yes, I will end it in 2 minutes. So, we can see, though see the bar, see the between these curves, they are the we compute the values. So we can see, uh, 3, 4, 5, 6, they are have similar curves, and the 1, 2, 3 have different curves. So the interaction features can detect the um, um, energy or the structure of this molecule. The another application is the colorography. This is the colorography. It is very important in plant. We can compute their features so far, even though they have similar structure, only different in a small part, but their interaction features are quite different. Thank you. That's
You ended suddenly. Okay.
yeah.
So thank you for your speaking.